Hi, my name is Guillem, and I'm going to present our work on learning a neural solver for multiple object tracking. In tracking by detection, our input is a sequence of RGB frames in a video and object detections for every frame. Our task, data association, is to link these detections into temporally coherent trajectories. Graphs offer a natural formulation for this problem. Nodes represent object detections, and edges possible temporal links among them. The task then becomes to identify which edges belong to actual trajectories and which edges do not. This is often done within a two-step pipeline. First, several sources of features, such as appearance and motion, are combined in order to define a set of costs over edges. Then, these costs are used within an optimization framework to select the final edges belonging to trajectories. This two-step approach has several limitations. To understand why, let's take a more detailed look at every stage of the pipeline. In the first stage, we typically consider every pair of detections and some spatiotemporal features, and then use a neural network such as Siamese CNN to output a score for the corresponding edge. In some cases, this is straightforward and appearance is enough to make a decision. However, in general, this can be a fundamentally ambiguous task. In this case, for instance, we see how we would want our network to predict that the first edge is less likely to be in a trajectory, as it skips a frame, while the first one does not. Since predictions are made independently for every edge, though, this becomes arbitrarily difficult. One way around this would be to explicitly encode relationships among pairs of edges. However, this would make our optimization problem significantly more complex. This brings us to the second stage of our two-step pipeline, using the edge cost we have defined within an optimization problem. Even without high-order terms, this is an integer optimization problem that can be hard to scale to large instances. Once we start adding high-order interaction terms, then this typically yields an NP-hard optimization problem, which is expensive to even approximate. Overall, we have a trade-off between performance and optimization complexity. We propose to tackle this trade-off with a novel neural solver that can implicitly encode high-order graph information and directly predict graph partitions. This way, we avoid the need for expensive discrete optimization without sacrificing performance. More specifically, we aim to perform both feature extraction and final solution prediction with a model that operates on the graph domain. To do so, we first embed appearance and scene geometry cues into graphs as node and edge embeddings. After that, we use a message passing network to propagate these embeddings across the graph iteratively. Finally, we take the updated edge embeddings, which now encode high-order information, and classify them into active and non-active. Let us now go into more detail for every stage of our pipeline. To encode appearance cues, we take every object detection and feed its RGB patch to a CNN that is shared across the graph. This way, we obtain an initial embedding for every node. For every pair of detections, we consider a set of basic coordinate-based features, time distance, and appearance similarity, to build a feature vector that we then feed to an MLP to obtain an initial edge embedding. After that, we start combining these embeddings via neural message passing. At each iteration, two updates are performed. In the first one, information flows from nodes to edges to update edge embeddings. It consists in combining each edge's embedding with its incident node's features via an MLP. In the second step, information flows from edges to nodes to update node embeddings. The standard way to perform this update would be to aggregate for every node all of its incident edges features at once, and then use another MLP to produce the new node embeddings. However, we propose to split this aggregation into two sums, one over nodes in past frames and another one over nodes in future frames. This allows message passing to encode the temporal structure of graphs. In our experiments, we observed that this simple change yields a significant performance boost. Repeating this sequence of updates several times allows our edge embeddings to progressively encode high-order information. When we initialize graphs, each edge only contains information about its pair of incident nodes. After the second iteration, it then has access to all the neighbors of those nodes, and so forth. Therefore, after a sequence of updates, we can then classify each individual edge while accounting for interactions across the overall graph. In our population studies, we evaluate the effect of neural message passing by training networks with an increasing number of message passing steps. We verified that this is the key factor driving performance, as all tracking metrics are improved significantly when we move from pairwise to high-order information. For benchmark evaluation, we test our models on the MOD 15, 16, and 17 datasets, and set new state-of-the-art results with a significant margin in all three of them, both in terms of MOTA and IDF1. Remarkably, we are also up to one order of magnitude faster than several graph methods. Please come chat with us if you have any questions, and check out our paper for further details. Thank you for your attention.